Happy learning! Today we're going to talk about spanning trees. Okay, so before we get to defining what a spanning tree is, we're going to first define what a spanning subgraph is. All right, so definition. We say that a graph H is a spanning subgraph of a graph G if H contains all the vertices of G but not necessarily all of the edges of G. Okay, so how do we write this mathematically? That's to say that the vertex set of H is equal to the vertex set of G, and the edge set of H lives inside of the edge set of G. Okay, so you can't make new edges. We're just going to take some of the edges of G. Okay, let me give you an example. So if G is the following graph, all right, so if this is G, and if this is H, then H is a spanning subgraph of G, right? They have the same vertex set. They both have A through G as their vertices. And H contains some of the edges of G and no new edges. Okay? So in this case, H is a spanning subgraph of G. And so what we're going to be interested in is not just subgraphs, but spanning trees. So what is a spanning tree? A spanning tree is a spanning subgraph that happens to be a tree. Okay, so remember what it means to be a tree. It means that the graph is connected and it has no cycles. So this is not a spanning tree, but if we got rid of some of the edges, now we do have a spanning tree. All right, and so today we're going to talk about two algorithms to find minimum spanning trees. So spanning trees, if we have a weighted connected graph, I guess, that connects the vertices as cheaply as possible. All right, so let's state the first algorithm. This is Kruskal's algorithm. Okay, so what do we need? We need a weighted connected graph. Okay, and so what does Kruskal's algorithm say? First step. The first step is choose the edge of least weight. All right, so find the edge in the graph that has the smallest weight. We are going to highlight it and include it in our tree. Okay, what is this saying? We're adding it to our tree. Our tree is going to be called T. We know what its vertex set is going to be the vertex set of the entire graph. And its edge set is going to be something we call E prime, which is just going to be a subset of the edges. Okay, so this is just saying we're building our tree. Okay, so don't sweat about the notation. And then step 2, which is like the main part of it, is we're going to repeat step 1. So long as no cycle is created. Okay, that is to say, just keep picking the smallest edge and just make sure a cycle isn't created. Okay, if adding an edge would make a cycle, we're going to skip it. All right, it's as simple as that. And so our output is the minimum spanning tree. Okay, note that if there's a tie, right, if two edges have the same weight, just pick one of them. It doesn't matter. You might get a slightly different tree, but it's going to have the same weight. So this is a very easy algorithm to run, and it's guaranteed to get us the minimum spanning tree. All right, let's do an example. All right, so we're going to apply Kruskal's algorithm to the following graph. All right, so these will be the vertices A, B, C, D, E, F, and G. All right, and so here are the edges, and now we also have to give it the weights. So 7, 10, 2, 6, 3, 3, 5, 1, 3, and 7, 2, and 7. Okay, so I encourage you to pause the video and try to solve this on your own. You might not get the exact same tree that I get, but as long as the weights match, you did it correctly. Okay, so let's go through and create our tree. We know that it's going to have all the vertices because it's a spanning tree. So I could draw in the 7 vertices already, and now we're good to go. I'm not going to put the labels, it just clutters everything. First step is find the smallest edge. That's this one. So we'll include that. Has weight 1. Okay. Next step is find the next smallest edge. So it's either 2 or 2. We're going to have to pick one of them. Okay, so let's pick this one. All right, now pick the next smallest edge, which is 2 again. So we'll pick that 2. The next smallest edge has weight 3. There's 3 options here. We could include any of them. So I'll start with this diagonal one. And then maybe we'll do this one for the next one, but it doesn't matter. We'll pick one, so pick this one. Again, at each step, we have to make sure we're not creating a cycle. And now, if we tried to include this last 3, what would happen is we'd have a cycle. You see that? We'd have a cycle, right, if we included this edge. So we can't include that. Trees have no cycles. So we're going to pass over the 3. What's next? 5. Again, if we were to include the 5, that's a cycle. We can't include that. So we're going to skip over the 5. What's next? 6. We can include that. All right, and since we've hit every single vertex, we're done. This here is the minimum spanning tree, and its weight is 6 plus 3 plus 3 plus 2 plus 1 plus 2. Its weight is 17. All right, so you could imagine if these were a bunch of desks in an office that had to be connected by cable to some central hub, 17 units is the cheapest we could do it. Okay, so if we have to connect all of the vertices to some network, 17 would be the cheapest we could possibly do. Okay, let's now talk about the next algorithm for finding spanning trees, which is Prim's algorithm. All right, so Prim's algorithm is similar to Kruskal's algorithm in the sense that we need a weighted connected graph, and our output is the minimum spanning tree. But it has the advantage of, at each step along the way, the tree that we're building stays connected. Okay, so this could give you a sense of, let's say this was like a road system that you're building. It would be pretty inefficient if you built this road first and then this road, because you wouldn't be able to travel from this part to this part. So having it stay connected the whole time has there's some applications where that's a nice property to have. All right, so the input, again, is a weighted connected graph. And it's another pretty short one. First step, another difference with Prim's algorithm is if there is like a central server that's where everything needs to be connected to, we start there. All right, so let V be the root. All right, so that's where our tree is going to start growing, right? That's how trees grow, is from the roots. Okay, if there's no root specified, just pick anything to be the root. Okay, so that's our first step. Step 2 is among all the edges incident to our root, all right, so out of all of the edges coming out of our root, we're going to choose the one with minimum weight. All right, so this is very similar to when we were doing nearest neighbor algorithm for Hamiltonian cycles, right? We were basically finding the edge out of our vertex that had the least weight, our nearest neighbor, okay? So same idea here. So out of all the edges out of our root, choose the one of minimum weight. We're going to highlight it. And add the edge to the tree. Okay? Now we're going to look at the set of edges that have exactly one of its vertices in the tree. So let S be the set of edges with exactly one endpoint in the tree that we've built so far. Okay, we are going to find the shortest edge in S. Okay, we're going to find the shortest edge in that set, add it to our tree, and then repeat this process. All right, and what is the output? The output here is, again, a minimum spanning tree. Okay, so like I said, the advantage to Prim's algorithm is that at each step along the way, this tree that we're building is connected. So it could give us a sense of like how we would actually build these roads or install the cables. So it gives us a little bit of an order to it. All right, so let's now, instead of apply Kruskal's algorithm, let's apply Prim's algorithm. Okay, and we're going to use A as our root because it comes first in the alphabet. We know our final tree is going to look, it's going to have our tree at the end is going to have all 7 vertices. Okay, so out of all of the edges that come out of A, which one's the shortest? That is this edge. All right, so we're going to include this edge. I'm going to also draw on our original graph just so we could kind of get a sense of this S set that we're talking about. So here we have A is highlighted. Okay? Now, out of all of the edges out of either A or D that don't have both of their edges in the tree, we need to find the shortest. So we have 7, 10, 3, 3, and 2. This is our shortest. So we're going to include this in our tree. All right, now notice that each step along the way, this graph stays connected. Okay, again, all the edges out of A, D, and G that don't basically make a cycle, we got to find the shortest. So it's either this 3 or that 3. We could pick either. I'll do this one for now. Again, all edges out of A, B, D, or G that don't create a cycle. So 10 would not be in this S set, right? Because this 10 edge has both of its endpoints in our tree. So we can't include it. Okay, we want to find the one with the least weight. That's the 2. All right, out of all of the edges that have exactly one endpoint in our tree, which one has the least weight? Well, it's this 3 or that 3. I'll go with this one. It doesn't matter, but I'll go with this one. And then finally, out of all the edges, yada, 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 it's the 1. Okay? So here is our tree. We have a tree, we have a spanning tree, and we can compute its weight again. It should be 17, right? We should get the same answer as when we did Kruskal's algorithm. And let's see. We have 6 plus 3 plus 3 plus 2 plus 1 plus 2. I believe that is 17. Okay, so this, hopefully you found this pretty interesting. This is just 2 different ways to find minimum spanning trees on a graph. Okay, so let me know in the comments if you have any questions. And otherwise, I'll see you in the next one. Take care. Bye-bye.